Hey guys, today we are talking specifically about infinite geometric series. So, geometric series that doesn't end. We keep multiplying the same thing over and over and over up to infinity. So, the sum of infinitely many terms is infinity in this case, when we have 3 plus 12 plus 48 plus 192. Notice we're multiplying by 4 every time, and so that number is going to continue to get larger, and so in this case, our answer is infinity. But if you look at the next example, 4 plus 1 plus 1/4 plus 116 plus 164, if we add all of those, the numbers are getting smaller, so it's approaching an asymptote. It's approaching a number. So the sum of one term, the sum of the first term in this case is just 4. The sum of the first two terms is 4 plus 1 is 5. The sum of the first three terms is 5 and 1/4 or 5.25. The sum of the first 4 would be 5.25 plus 1/16 more, which is 5.3125. Sum of the first 5 adds another 64th on, so 5.328125. You can see that it's headed towards a value there. It's just something a little bit above 5. And so we can see as we add more numbers on that it is approaching a certain value. So the sum of an infinite geometric series can be found using this rule. So our first term divided by 1 minus our ratio. And this only works if the absolute value of the ratio is less than 1. So if it's greater than or equal to 1, just like we saw in that first example, the series will not converge and there is no sum. It goes to infinity. So then let's find out what this term really is if we want to find the sum of an infinite number of terms. So our R value, what are we multiplying every time? Well, remember you can always divide backwards if you don't know. But we're multiplying by 1/4 then. So we want to double check, is our R value less than 1? And it is, since it's 1/4. So then the sum is equal to the first term over 1 minus the ratio. So then we get 4 over 3/4, and remember when we have complex fractions, fraction within a fraction, we flip that over, so that's the same as saying like 4 times 4 over 3, or 16/3 is what that converges to. 16/3 is the same as 5.3, repeating 5 1/3, and you could see that that's where that was headed. I think it was 5.328. was where we had gotten to with just adding the first 5 terms. So, important kind of way of writing here, S sub n is a finite number of terms. So this notation is important. Whereas S without the subscript is an infinite number of terms. Those are different things. You need to know which you're referring to by saying S sub n is finite, S is infinite. Okay, so for example 2, let's find the sum of this infinite number of terms. So what this tells us, here's our rule, and notice it's in geometric form. So our A sub 1 here, our first term is 2, and our ratio that we're multiplying every time is 0.1. So then S equals first term over 1 minus our ratio. So then we get 2 over 0.9, which is 2.2 repeating. All right, let's try another one. So we have 12 plus 4 plus 4/3 plus 4/9. So our first term is 12. Our ratio, we're multiplying by 1/3. So S is equal to 12 over 1 minus 1/3. So that's 12 over 2/3, which is the same as saying 12 times 3/2, which is the same as 18. So that one converged to a nice whole number 18. Okay, we can work backwards here. Find R in an infinite geometric series with a sub 1 equals 5 and a sum of 27 over 5. So here we know our answer is 27 over 5. We know our first term is 5. We want to know what our ratio is. So I think the easiest thing, since it looks like a ratio is equal to a ratio, we have proportions. We can cross multiply. So we get 25 is equal to 27 times 1 minus r. We cross multiply. So then we get 25 equals 27 minus 27r if we distribute that out. Subtract 27. So negative 2 equals negative 27r. Divide by negative 27. So we get r is equal to 2 over 27. And that's all it asked you for. Okay, writing a repeating decimal as a fraction. So if x is a repeating decimal, then x is rational. We know that when we have repeating decimals, those are rational numbers. So let x equal the repeating part of the decimal. We're going to rewrite x as a geometric series. We want to find the sum of the geometric series as a fraction. And it's an infinite sum because since it's repeating, it never ends. We're going to add to the sum any part of the decimal that did not repeat. So here's an example. We have 5.41 and then 6 repeating. We want to rewrite that as a fraction. So step 1, let x equal the repeating part of the decimal. So x is equal to 0.006666. So step 2, rewrite as a geometric series. So 0.006 plus 0.0006 plus 0.00006 and so on. If I added those together, that would give me that repeating decimal. So step 3, we are writing it as a geometric series. So S equals, our starting value is 0.006 over 1 minus, and to get from 0.006 to 0.0006, I'm just multiplying by 1/10. I'm multiplying by 0.1. So that means it's 0.006 divided by 0.9, which if I just move the decimal place over, if I move it over 3 places to get that to be a 6, I move it over 3 places here, that would be 900. Reducing 6 over 900 would be 2 over 300 if you saw that divided by 3, but that'll go even further. So 1 over 150. So then we need to add on the other stuff. So we had 5, and then we had 0.41, which is 41 hundredths, or 41 over 100. And then we had 1 over 150 was our repeating decimal part. So to get these to have the same denominator, I'd take it back to 300. So we have 5 plus, so over 300, I need to multiply 41 by 3, that's 123, and then that was 2 over 300. So then I get 5 and 125 over 300, which does reduce to 5 and 5/12. Remember to take that back to a mixed number. We multiply the denominator by that whole number 5. So 12 times 5 is 60 plus the 5 parts. So we get 65 over 12. Either one of these would be an okay answer. So that's how to show all of the work to write a repeating decimal as a fraction. You put 65 over 12 in your calculator, you will get that decimal back out. All right, let's try another one of these. So, we're going to leave our 4 alone because it's not part of the repeating, but we have 372, 372, 372. So then our rule, 372 plus 0.000372 plus 0.0000000372, and so on. So we need to know our ratio here. What are you multiplying every time? Well, you get 3 more zeros. So we're multiplying by the thousands, tens, hundreds, thousands. So then our first term is 0.372 over 1 minus 0.001, which is 0.372 over 0.999. So we get 372 over 999, which is 124 over 333 if we reduce that. Then we need to bring this 4 back. So 4 plus 124 over 333 is 4 and 124 over 333. Remember, 333 times 4 plus 124, that's 1456 over 333. Alright guys, that's all I have for you today. If you have questions, feel free to come in and see me. Otherwise, I will see you in class.